Yeah, thank you very much, Sylvia. I would like to start my talk thanking the organizers for the invitation. It's a great opportunity to be here. It's nice to see old friends, and it's also nice to see new people, new faces, and it's my pleasure to be here. So just to picture me correctly, my background is not so much on oxides. My background is more on metals. My background is something about spintronics. So I'm thinking about transport, electronic structure, spin, magnetization, but always in the context of something conducting, something metals. I think about complex magnetism, about frustration, about skyrmions, hopfions, these kind of things. So not so much about oxides myself. In some sense, my talk is a continuation of Ole Eriksson's talk. If you have Ole Eriksson's talk in your mind, you can kind of relate to my talk. And before I continue, I would like to thank all the people who contributed to this in one way or the other. Especially, I would like to mention Daniel Wortmann, Gregor Behalicek, and Christoph Friedrich. They are responsible that our codes are developing and running. And I would like to mention in particular also Jura Mokrusov. He has all this knowledge about topology and Barry phases and transport and spin transport orbitronics, which he develops together with Don Woog and Frank Freimuth and Jan Philipp Hanke. And you see Mariana here, and she will give a talk later in the afternoon. And with Hiroshi Katsumoto, did all the spin models, which you see in this talk. All right. So I would like to give a leisurely introduction to the spin orbit in the valence band. That's all. You have seen this already. I just remind you the spin orbit interaction is in principle a small thing. And here you see, for example, the band structure of a semiconductor without spin orbit coupling, and you see the band structure of a semiconductor, here germanium, without spin orbit coupling and with spin orbit coupling. And there are tiny differences, and these tiny differences are located here, where you have, for example, a split of state from a P3½ to a P1½ state. And you see the splitting is about 30 millieV. And basically, the spin orbit interaction, the strength is somehow proportional to a nuclear number square. And therefore, so you see for diamond, which is carbon, the splitting is in the order of 6 millieV. And gallium arsenide is in the same row as germanium. So the splitting is about the same. So it is a small effect in the valence band. It also, in metals, if you don't think about 4F metals or 5F metals, but in typical 3D metals, the orbital moment is quenched. And the spin orbit interaction leads to the unquenching of the orbital moment. So basically what it is so the spin orbit interaction is all in the wave function. And the wave function changes due to the spin orbit interaction. And the change of the wave function, if you take then the expectation value to the orbital operator, it is not anymore quenched. And you have a finite orbital moment, a small one, because the spin orbit interaction is small. And you can also get the energy of this. This is the spin orbit energy, which is contributing to the magnetocrystalline anisotropy energy, which is then, so to say, second order in the spin orbit interaction. And the denominator is the energy difference between unoccupied and occupied. And this you have seen probably in the lectures already before that people write down energy functionals for the energy of the magnetic anisotropy. So this goes on and on and on. So this is this is sine square and sine 4 square, for example. And then you see the sine square is proportional to the magnetization square, and the sine 4 is proportional to the magnetization fourth power. And that relates actually to the perturbation theory, which you have to do in the prefactor. And then you see the higher the order, the higher the perturbation you need. And for example, here you have the fourth power over the third power. What does he tell you this? What does it tell you this? It tells you, if this is if you have, do we have chalk here? Actually, yeah. Imagine you have a band, and you have here the occupied state and the unoccupied state, and you make an spin flip excitation to here. This energy matters. Since this energy, delta E, is to the power 4, the higher the power, the more only matters around the Fermi surface. And therefore, the Fermi surface is a very critical thing, and any choice of U changes your Fermi surface and changes these numbers. And the higher the power, the more it is affected. For example, here you see, if you calculate the energy scale is in the typically 20 to 30 micro EV to 2 millieV. You do all these efforts and all these perturbation theories and all this spin orbit only for these small numbers, but these small numbers matter really. And actually, I showed you now 2 examples, but in reality, the spin orbit interaction has a lot of fascinating realizations and ramifications in solids. So I have here a list where the spin orbit interaction enters, and it's important. I had to stop because the page is full, but it has the Rushbar, the Dresselhaus, the Edelstein, the magnetoelectric effect, magnetic anisotropy, orbital movements, orbital currents, magnetic dichroism, spin orbit torque, Dzyaloshinskii-Moriya interaction, and so on, all the Hall effects, and so on. So this is a really very important quantity, and there is an entire community who tries to get answers to these questions. And I will not be able to go through all this list today. Some of these effects have nothing to do with magnetism. They are just spin effects, so they are also present in non-magnetic solids, such as the Rushbar effect or topological, or the quantum Hall effect, or the topological Hall effect, some spin relaxations, Gilbert damping. For that, you don't need magnetism at all, but you need spin orbit interaction. And with this spin orbit interaction, as small as it is, it defines a great field, which is spin orbitonics, and nowadays also orbitronics, where it controls the topological nature in a momentum space. It controls the topological nature in real space, and it controls the driving of spin textures due to currents using spin orbit torque, for example. I will give you now a small example where the spin orbit interaction, where you can actually feel the spin orbit interaction. Starting with bands without spin orbit interaction, you have a Kramers degeneracy, you have two states, up and down, doubly occupied state, and your wave function might be given as shown here. You have a spin up wave function, a spin down wave function, that's it. But if you have spin orbit interaction, of course, the spin is not a good quantum number. Some of the spin up spin is actually projected onto this spin down amplitude, and vice versa. And typically for the spin up wave function, this parameter A is large and the B is small, and for the spin down is the opposite. And this parameter, which is called the Elliott-Jaffet parameter, you can also get in perturbation theory exactly the same way. You have spin flip transitions. This is the strength of the spin orbit interaction. And this basically gives you then a splitting of this band. And for example, the splitting of these bands is not everywhere the same. And if you look at the Fermi surface, there are certain points where the splitting is extremely drastic, where this B value K is extremely strong. And for example, here I have an osmium surface. Of course, I choose osmium because of the gigantic spin orbit interaction. And so you have a Fermi surface of osmium. And now it turns out that this Elliott-Jaffet parameter, or this Fermi surface, depends on the magnetization direction. I inject electrons into this osmium, and depending where I inject these electrons with which K vector and so on, I have now very different lifetimes, and the lifetime is the inverse of the lifetime is proportional to this spin lifetime, this Elliott-Jaffet parameter. And if I take, for example, spin up or polarization in Z direction or polarization in X direction, you see the strength of this parameter beta B is very, very different. And therefore also you have a strong anisotropy of the lifetime in this material. This you can actually see by a Gedanken experiment, which became actually real as a real experiment. So you have, for example, one of these osmiums here, or tungsten, or whatever is heavy, with crazy Fermi surfaces and hotspots. And then what you do is you put a metal, a ferromagnet on it, and you inject a spin polarized electron in your system. And then you have a detector, and you ask yourself, how strong is the spin polarization? If you do that, you get something like a spin diffusion. The further you away, at a certain point, it has relaxed to zero. And you can do that in different directions, and you see the exponential is different. And there you really see that you have an anisotropy in the spin flip lifetime. If you now assume that you have spin-orbit interaction and you have space inversion symmetry, then you can even show that the states remain degenerate. If you have time inversion and space inversion, you see that this wave function and this wave function have the same energy. But if you have now a broken inversion symmetry, then when you have only time reversal symmetry, this trick here does not work anymore. And at a given k point, you have actually a spin splitting. And this spin splitting, the electron does not know where the spin splitting comes from. It assumes there is an internal magnetic field, and that's the other thing that spin-orbit interaction can do in non-central symmetric systems. It creates a magnetic field, a k-dependent magnetic field, and this k-dependent magnetic field leads to a spin splitting, and this spin splitting you can detect. It is basically detected in a typical Rashba effect situation. So you have a surface, and this surface you have electrons running around, and these electrons have a head and a tail. So the tail of this electron feels the surface. It feels the broken inversion symmetry. And this tail, when it feels the broken inversion symmetry, effectively, it feels like something like an electric magnetic field. It feels the broken inversion symmetry, and you get this Rashba kind of term. And this Rashba effect you can actually see as the broken, as the spin splitting of a surface state. And this is, I think, calculated. This is the old experiment by photomission. It's a relatively good agreement. I don't worry about this currently. And this you can, for example, use then for transport experiment. Question is now, I talked about the tail of this wave function, which probes the non-sphericity of the potential and feels the non-sphericity of the potential. But where's the spin-orbit interaction coming from? So what we have, we can ascribe spheres around our atom, Marfan-Tin sphere or atomic spheres and so on. And now what we ask ourselves, where in this sphere is actually the strength of the spin-orbit interaction? And if you do that, so you calculate your spin-orbit matrix element, this is this psi, and you have here a radial dependence, and you integrate this out from 0 to the edge of the boundary. And if you do that, you realize that 99% of the spin-orbit interaction comes from already from a very, very small region in the Marfan-Tin sphere. So basically, the strength of the spin-orbit interaction is produced by the head of the wave function, which is running like crazy with crazy kinetic energy around the nuclei, and produces the strength of the spin-orbit interaction. And this you see here, for example, I plotted here the strength of the spin-orbit interaction as function. So the measured, what I'm measuring is the splitting of the Rashba state as function of the radius, and then you see already at maybe a quarter of atomic unit, sphere radius of an atomic unit, you have already reached 99%. The same way you can ask yourself, so this is the head of the wave function. But you can also ask the tail of the wave function, which is probing the non-sphericity, the broken inversion symmetry. So what is the contribution of each layer? And you see 60% comes from the first layer, and then you really see how the contribution, the sphericity of the potential, the broken, the broken inversion, broken potential feels, the electron feels less and less of this. On inside, it is then no contribution anymore. All right, now we apply the same thing to magnetic solids. So here is iron. We have seen iron in the talk of Ole Eriksson. And this is without spin-orbit interaction. And you have here a spin splitting. You see these states, and these states are in parallel. This is spin down, and this is spin up. This is majority, this is minority. If you switch now on the spin-orbit interaction, what you see is some of these degenerate states are lifted. The lift is small, but this depends actually on the ESI axis of the magnetization. Now this effect is small, and maybe it is not important, but in reality you can see it experimentally. You have to tune your system a little bit. So what you do is, I take two monolayers, iron and tungsten. This is ferromagnetic, and this is the band structure. Don't look at it. But what you see is I plot this here, larger here is this, and I'm focusing more or less on this point, because this point here is at a Fermi energy, and in the Fermi energy you can see a lot. And now you see, if you look very, very carefully with spin-orbit interaction, it is different for in-plane and out-of-plane magnetization. So what we can do now is we focus on this point and look at the density of states. I look at the density of states in the vacuum of this out-of-plane, and here I look at the difference of the density of states in the vacuum between out-of-plane and in-plane as function of the energy. So I'm starting here, so from below. And then you see you have contributions. You see the differences between up and down, out of plane and in plane. And these differences become noticeable if you go through the Fermi energy, because now you are here, and then it becomes smaller again. And now you need some friends who do experiments. How can you do an experiment where you have out of plane and in plane? This is when you have a domain wall. So imagine you have a situation where you have a domain wall, you have a domain wall, and domain. In the domain, on the domain wall, you actually rotate the magnetization from out of plane to in plane. And what I demonstrated is that this density of states depends actually, due to the spin-orbit interaction, on the magnetization direction. And if I take this magnetization direction, so that means also my tunneling current depends on the magnetization direction. And I think what we are showing here is the tunneling anomalous magnetoresistance which we use for imaging here. And so this is the experiment. You take a tungsten surface, you have a small miscut, you have steps, you grow iron on top of it. You have layers of you have two layers, and you have wires of 2 layers of iron and wires of 1 layer of iron. The topography is seen like here. And here you basically see the spectroscopy at a certain bias voltage. And what you see here is basically some color, which is the tunneling current. And you see here some black stripes. And this black stripe is actually the domain wall. And everything is measured with the tungsten tip. There's no magnetic sensor or something like that. So basically, you really use here the spin-orbit interaction to probe, to change the tunneling conductance. And this has been the experimental, the effect is of course small. Our experimentals have good eyes. And so what we see is you have the spectroscopy here for in the wall and in the domain. And the main difference is this one. And then you normalize the difference and blah, blah, blah. It becomes a little bit larger. And then we can compare this to our theoretical calculation and find the comparison to it. All right. Now, maybe you'll get carried away with these cone sham bands and this is non-interacting electrons. But I would like to remind you that electrons are interacting. And as nice as these cone sham bands are, we have to realize that these electrons, which are responsible for the magnetism, they also create have excitations and they create other things. For example, magnons. And you here see the magnon dispersion for iron calculated in something which is called the Bethe-Salpeter equation. This is basically a two-electron equation because a spin wave is a coherent superposition of spin-up electron and spin-down electron of different spins, different spin direction. And you have something like Stoner excitation. This is the single particle excitations, and you have the magnons, and sometimes the magnons runs into a Stoner continuum, and then they become broad. And what you see here is, for example, some excitations are Stoner excitations, and they interfere with the magnon excitation. Here, the dots here are the experiments of Collins and Moog. And now, so your conduction electrons, d electrons, which are responsible for the magnetism, create this. It is obvious that this interaction of these d electrons with these magnons should be also seen in your spectrum of the electrons in the band structure. And this we looked at, so we combine, we extended our GW calculation, including the plasmons, conventional GW, and we included the scattering on the magnon. And then you see here in red, you see the DFT lines, the DFT band structure of non-interacting electrons. And here you see the band structure of interacting electrons. You see the lifetime broadening, which is this colored thing here, is completely different from majority electrons and minority electrons. This we can understand. And this is also seen in experiment. The minority is, for example, much sharper than the majority. We can argue maybe that the majority has maybe no bands anymore. And this has also implications because if an electron runs through the system, makes a Stoner excitation, and at the same time feels the magnon, you have something which we call a kink structure, but not in the regime of 500 millieV or 400 millieV. You can also have the kink structure rather deep because the Stoner excitation has large energies. And you see in the minority state, in the majority state, sorry, wrong character. No. Yes, that's right. Yes. One is this is the correct approximation, and this is the wrong approximation. It looks like the majority state in the right approximation. Yeah, and you see here that here you have so to say, the interference of the electrons with the magnons. This changes as a, so to say, hybrid crossing. This you can see also in the experiment, actually, at the same energy. So I think the cone sham bands are super. We understand a lot, but we need to spectroscopy, maybe don't take it for real. Now I should slowly, so I had spin orbit interaction in the title, I had magnetism in the title, and density function theory in the title, so I have to switch now to magnetism. So we learned from Ole Eriksson that if you want to understand magnetism, maybe it is good to write down an atomistic spin lattice model, the Heisenberg exchange, or Dzyaloshinskii-Moriya exchange, or magnetic anisotropy, and dipole, and coupling to external fields. And all this is a classical spin model. So these are classical vectors, three-dimensional vectors. Usually I normalize them to 1. And so my prefactors are also normalized in a certain way. In metals, they are typically long-ranged, and in insulators, they are typically short-ranged. And now what we go, now so this is, so to say, writing something down according to physics. What we can do is now, we can do a long wavelength approximation. This long wavelength approximation, this leads you to this micromagnetic model. Out of this, the Dzyaloshinskii-Moriya interaction and the magnetic anisotropy, of course, are spin orbit dependent quantities. And in this formulation of the micromagnetic model, you have basically a huge contraction of information, because here you have all the information of the lattice, the interactions, and you contract this to a number, which is the spin stiffness, or you contract this to a number, which is the spiralization tensor. But the nice thing about this smooth representation is that it's basically a field theory. And in the field theory, you can do, it is smooth, and you can relate this to topological objects. And that's actually the way we relate to skyrmions and Hopfions and skyrmion strings and whatever it is. And of course, our job is to somehow, you know, getting electrons are fermions, and these fermions somehow producing these spin models, the spin interactions. And I think it is important to somehow understand how do we get this the strength of these interactions. So the way I'm seeing it is basically we have a fermionic system with billions of electrons, but we go ourselves in a low energy region of our Hamiltonian, where we basically integrate out all these fermionic degrees of freedom, and what's left is, so to say, the spin interaction. And this we would like to get from density functional theory. And of course, since this is dependent on relativistic, we have to go to the relativistic density function theory to get these parameters. There are many ideas how to do that. One can think of that somehow we map out a total energy landscape, and by mapping out the total energy landscape, we somehow maybe can expand this model according to this energy landscape. I would like to say that although we write all the same Hamiltonian, depending for which you want to apply this Hamiltonian, you might get different prefactors. Because there is in principle so to say, an initial state dependence. It is different whether you want to say, I want to get the low temperature regime, the spin excitations in the low temperature regime, or you say, I want to get the Curie temperature where already all spins are basically disordered. Because in both situations, so to say, the initial state from which you expand your parameters might be very different. It is a nuisance. So the first question I would like to address is this actually the right Hamiltonian? And or can we have other situations? If you look now in the literature, it's the last 10 years, I would say, there are a lot of experiments here, and there, where you actually see this Hamiltonian will not give you the spin structure which you imagine. Or no, not which you imagine, which you detected experimentally. And you have this biquadratic exchange which you need to improve the spin stiffness, to improve the magnon dispersion of iron. You have foresight, three-spin interaction to describe this experiment, the magnetic structure of iron and rhodium, and so on, And and I have to say, for each of these kind of exchange interactions, which are all isotropic, you have also a related Dzyaloshinskii-Moriya interaction. So for the Heisenberg interaction gives you the Dzyaloshinskii-Moriya interaction if you include spin-orbit interaction. But the chiral, the biquadratic interaction gives you this chiral biquadratic interaction. Or, for example, the four-spin three-side interaction gives you this type of interaction here. And so basically we can describe all this, but basically we have a lot of interactions. And what frustrated me personally is whenever you have a new experiment coming, you need a new interaction. Not always, but sometimes you can only explain things with a new interaction. And this is boring. I mean, this is not universal. I mean, so this annoyed me. So we had to think a little bit, I should say, maybe I should also say, give some examples. So this is, for example, a magnetic structure we call the magnetic skyrmion lattice, is iron on iridium, experimentally detected. It is a square lattice. The square lattice is not the square lattice of atoms, it's the square lattice of the skyrmions. And you can only understand this structure if you have this four-spin interaction. Or you have here, for example, two different experiments. One is manganese on rhenium. This is also manganese on rhenium, but this has a FCC stacking. This is an HCP stacking. In this, you get a single Q state, and here you get a triple Q state. This triple Q state is also related to this higher order spin interactions. So the question is, how do you get all this? How do you get all these spin models? And do we have a final spin model system generator? And I remind you of the work of 1929 or 28 of Heisenberg and Anderson come later, but Heisenberg in 28. So what he said, yeah, this exchange interaction is an exchange interaction because you have the exchange of electrons, which are indistinguishable particles. And so basically, so if you have a many-body wave function and you exchange the coordinates of two electrons, basically you change nothing, but maybe you get a different sign. And so basically, if you have n electrons, you can have n factorial permutations. This is a lot. And for each of these n factorial permutations, you can calculate a Coulomb interaction. And the only thing which you take out is the unity, because this gives you basically the Hartree chart. Then basically you can now group, first of all, before you exchange all electrons, you exchange maybe 2 electrons. You exchange 3 electrons, you exchange 4 electrons, you exchange 5 electrons, and so on. And at the end, you can write down your spin Hamiltonian as a number of permutations. You have to take care on the sign, times an interaction strength. And you know how permutation works. So if, for example, electron 1 is in spin up and electron 2 is in spin down, if you permute, it's the opposite. And then you can, for example, if you exchange 3 electrons, then you can have 6 permutations. 1 you take out because the 1, then you can the other decompose into transpositions and 3-side permutations. You can go to 4, and so on. And at the end, you can write down your total exchange Hamiltonian as permutations over classes and things like that. And now, the only thing what you have to know is how to represent the permutation operator by spin operators. And this depends on the length of the spin. For spin half, the representation of the projection operator, of the permutation operator, is simply this dot product. But if you have spin 1, it is a dot product and dot product square. If you have 3 half, it goes up to 3 power. And now what you have to do is, basically, you have to put this into here, and that's all you need to know. And this you can generate a lot of spin models. And I exercise this here for spin 1. So you have 2 sides. You get Heisenberg plus biquadratic. Then you have to generalize this for the crystal. And for 3 side, you get then Heisenberg biquadratic, 4 spin 3 side, 6 spin 3 side, and so on. And now you have to think a little bit. Now it's a critical moment, and I have no answer to this question, but maybe it's worthwhile to think about it. If you have so this is a rather abstract model, but gives you the right form. But you can also study other models, more fermionic models, like the Kondo lattice model or the Hubbard model. And you come to the same form. And what you see, if you have spin 1 half, an electron is hopping. But if you have a spin 1, 2 electrons have to hop at the same time. And the question is, if you do now the classicalization of all this, so we replace the operators here by vectors, we have to ask ourselves whether density functional theory has the power to describe the prefactors of the spin 1, because it has to simulate the hopping of 2 electrons. This is not clear to me personally. Maybe I'm thinking one should start maybe with a beta-salpeter equation, which is a 2-electron equation, and study the contribution of the 2-electron hopping to these J's. I have not done this, but of course, we calculate things. But the question is whether we catch always the right physics is not clear to me. So this is deviation, and this is my message, main message of the day, because you are young people and you can solve these problems, you can think about it. Okay, now I want to calculate all this by density functional theory with a caveat that I'm not 100% sure whether density functional theory can manage always the concerted hopping of electrons 2 or 3 by 3.5. In any case, we know what we have to do. We have to do the relativistic density function theory. The relativistic density function theory, this has been worked out by a few papers. I recommend the paper of Alan McDonald from 1979. Everything is very nicely written up. You can follow this. But the problem is, so in relativistic density function theory, the main variable is not the density. The main variable is the forecurrent. It's basically the ground state for a Dirac current. That means we express interacting Dirac field with the external quantities by the vector potential. This is the 3 component of the current. This is the 1 component of the current, which is the density. And we have a universal functional, which depends basically on the forecurrent. If you go through the Kohn-Sham machinery, at the end of the day, you need an exchange correlation kernel or exchange correlation functional, which depends on this forecurrent. And yes, and I'm waiting for this successful approximation. Maybe our next speaker has a good idea about this. I don't know. Currently, I'm belonging to those people who have not a good idea, and therefore I'm basically working with very conventional spin density function theory. So I'm going back to the old paper of von Barth and Hedin. Basically my my ground state quantity is a spin density matrix, which is basically has 2 by 2 matrix with 4 entries, for quantity field. And this determines uniquely the potential and the external magnetic field. And this density matrix can either be written in this way, and if you look very carefully, it has also imaginary parts. You can imagine already that this makes it, the emission makes it more expensive than real. And the density can be represented either by the vector magnetization density and the charge density, or directly here. And as according to Kohn and Sham, we can express these densities by a non-interacting Kohn-Sham spinners. This is the true spinner theory. And basically, the density can be expressed according to these spinners. And what we do is basically we try to find this density matrix, which minimizes the ground state properties according to this functional. And in this universal functional F, that's where actually this relativistic enters. Relativistic enters in this theory mainly through the kinetic energy, which is part of this universal function. It is different from saying this is a relativistic theory. And I should say a few words about the treatment of the relativistic. Now, experimentalists can relax. So basically, in one way or the other, either when you construct pseudopotentials or if you construct basis functions, you have to express a wave function in the basis. And in this basis, we have to get a connection to the relativistic kinetic energy of the relativistics to the Dirac equation. And in many cases, in one way or the other, it falls back to solving a radial problem, and where the basis function has a large and a small component. And so basically, this is an angular momentum function. And this leads basically to a radial Dirac equation for this function, for this large and this small component. And most of the time, sometimes we solve it, most of the time we don't solve that. It has a couple of small complications, because especially if you work in a magnetic field. And we do instead something else. We approximate this by this two-component Kerning-Hamel formalism called scalar-relativistic approximation. So basically what we do is we average over so we call it the kappa index, basically the index of the representing the state in this radial wave function by L, and so to say by one, for example, P1/2 and P3/2. And then by averaging over, we get something which looks familiar to Schrödinger, and an additional term which is, so to say, this spin orbit contribution the spin orbit contribution to the Hamiltonian. So this is a kind of a perturbation. And this perturbation we solve actually, this Hamiltonian we solve actually self-consistently because this is the effective potential. And here's also the effective potential. And we call this the atom-centered approximation. And for example, by this, you can also, having this relativistic theory, you can, for example, calculate the orbital moment. And usually we evaluate this part in the Hamiltonian only inside the sphere. Also, when you construct the pseudopotential, it is evaluated into the sphere. And usually the regions between the sphere, the spin orbit interaction is not calculated. But we can calculate it, and this is about 1.5% of the entire spin orbit interaction in the sphere. I would like to say this is a nice, that's what 99% of the people do, but it's absolutely not correct. It is not correct in a solid, because in a solid, you have a translational symmetry. And the R operator, which you have here, is not the right operator in a periodic domain. And therefore, you have to apply, in principle, the modern theory, which we learned from the polarization. The modern theory of polarization is actually the one which we should use to calculate spin orbit dependent properties in a periodic solid. But most of us use this atom-centered approximation. We calculate, so to say, an atomic spin orbit interaction around the Magnetization sphere. As I showed you, we have already in a small radius 99% of the spin orbit. It's not fully correct. Sometimes we also do an error because the P1/2 and P3/2 wave function can be very different. And since we have averaged over, the radial dependence can be different. Sometimes it is better to add somehow in your basis set a P1/2 or P3/2 orbital to get this radial dependence. A famous example is a SLAT, and there's a recent paper about this by the group of Claudia. All right, so what we do is basically we have our Hamiltonian. This Hamiltonian in a certain basis becomes a matrix. It has a block diagonal parts which contains, so to say, parts which are diagonal in spin and parts which are depend on off-diagonal parts which are only in the spin-orbit interaction. There are various ways of solving this. So in the last 2 years, we went over, we changed it and we simply diagonalized the matrix, and that's it. But you can also, what is also done in the literature, you can see is that people block diagonalize each block individually, collect the eigenvalues, and then set up a second variation problem where the space is much smaller because the spin-orbit interaction is a weak interaction. And then you can probe the quality of your result as function of the subspace. This is, of course, a much faster procedure and runs under the name second variation is also self-consistent. But the calculation approach is different. And so basically we use the first variation in DFT, but we use actually the second variation for relativistic GW calculation. So basically we first do the GW calculation, diagonalize this GW, we get the eigenvalue spectrum in the GW, and add in the spin orbit interaction. And continue. And you have to be careful when you're doing what you're doing. So currently, most of the ab initio calculations done in GW with spin-orbit interaction is such that you first do an LDA calculation without spin-orbit interaction. Then you do a LDA calculation with spin-orbit interaction and take the difference of both, keep it in your mind. Then you do a GW calculation without spin-orbit coupling, plot your GW band structure, and simply add the SOC on top. And this gives you a different result than doing a first LDA with SOC, and then add, then do GW with SOC, as I described. The differences you see here, here you see, this is the structure of bismuth telluride. So at the gamma point, you see in green is the LDA result. In red, you see the GW plus SOC result, which is this one. And in blue, you see GW SOC and G SOC, W SOC. All right, I would like to make one last remark. If you do relativistic and you have magnetic moments, then you can also do, of course, you can always do perturbation theory, expand in the order of 1 over C. And if you do that, you get an interaction called a bright interaction. And this bright interaction shown here, you can massage a little bit, and you can extract out a dipole-dipole interaction, which looks like that. And this dipole-dipole interaction, yeah, you should solve in density functional theory. That's what we do. What we simply do is, we look at this and say, I take now the Hartree approximation. That means I replacing this sigma by my magnetization density, and calculate this thing externally by another program. I just take the magnetic moment out, calculate the energy as function of the direction of the magnetization. Yesterday, we had a discussion about these antiferromagnets. So if you have an antiferromagnet, of course, this is 0. But it's only 0 if your magnetization density is spherical. If your magnetization density is not spherical, you have a small quadrupolar, octopolar, whatever contribution. But anyway, this is the Hartree approximation. As a density functional theory person, you would not take a Hartree approximation. You would take something better, maybe a Hartree or or a Hartree-Fock, or even Hartree-Fock plus correlation. And this has been worked out by Hardis Gross group in Halle at that time. And he looked at corrections to this. As far as I can understand, these corrections are relatively small. All right, so we are going back to our conventional spin density functional theory. After that, you may wonder whether this works at all, but it's very powerful, of course. And so we have a vector spin density. The vector spin density is obtained self-consistently. You have by a self-consistent calculation, you get the charge density, the vector spin density, the size of the magnetic moments, the direction of the magnetic moments, the total energy. If you look now, this is a particular example. This is manganese on copper 111. You see this is the vector spin density, and you see, if you look very carefully, so this is where the atom is. The atom is located here. The magnetization in average points in this, and this, and in this direction. And you see there is very, very little non-collinearity. The non-collinearity is only at these edges here. So in first approximation, you could say, the intra-atomic exchange is so strong that everything is here in parallel. And this is particularly a good approximation here for when the local spin moment is large, when the inter-atomic exchange is large, and when the spin-orbit interaction is small. This is true for 3D metals, for 4F metals. And but it's not true for this modern material everybody's hot on, like the Kitaev material, ruthenium trichloride. And here you see, this is an image from Mariana. This approximation that everything points in the same direction inside the sphere definitely does not hold. This material has a magnetic moment of 0.14 Bohr magneton, so it is certainly in a regime where the local magnetic moment is small, the interatomic exchange is small, and of course the spin-orbit interaction. Since this is a 4D metal, the spin-orbit interaction is already relatively large and comparable to the exchange. But this is in general true for magnetic p orbitals for 4D, 5D, and 5F metals. And it has really consequences. So for example, this is calcium iridate in the antiferromagnetic G structure. And what the calculations have been done like this that really the magnetic moment is constrained to be collinear. But one calculation is collinear, has a collinear intraatomic approximation, and the other one has a non-collinear intraatomic magnetization. And you see the band structure here is totally different. So it has an effect actually on the band structure of this material. So these intraatomic collinear approximation works well for these 3D materials, manganese, iron, cobalt, nickel, blah, blah, blah. But if you work with p electrons, polarized electrons, you have to be very careful. Okay, I'm currently staying in this formulation. So I have a unit cell around my atoms. I have spheres, and these spheres maybe point, most of the atoms point in one direction. Most of the spins of this in this atom point in one direction. So I can take this atomic standard approximation. I have a global quantization axis in my system and relate everything to this relate this local quantization axis to this global quantization axis. Here in the sphere, globally, and at each point in this interstitial region. And since I don't know very much about my exchange correlation potential, what I'm doing is I take the exchange correlation potential actually of the homogeneous electron gas, and there I know only one component. So therefore, in the exchange correlation potential, the exchange correlation B field in this approximation is actually parallel to the magnetization density at each point in space. So basically, what I'm doing is I go into the code, I go into my unit cell and look very carefully how do I have to rotate the local quantization axis such that actually locally it is a spin up and spin down situation. There I can exactly calculate my exchange correlation potential, and then I rotate back into the global frame. And this I do also for GGA, where I take the gradient then in this rotated frame. Okay, the next step is I have now calculated everything. I know everything. I know my spin model and so on. I would like to understand now the magnetic metastable or the ground state. So I start, the funny thing is, the classical Heisenberg model in the periodic lattice has an exact solution, which is the spin spiral. So that means any spin spiral diagonalizes this classical Heisenberg model. And if I do that, basically I can minimize, I ask myself, what is the energetic minimum of this Heisenberg model? And then I see, yeah, the energetic minimum is when I minimize, when I take this spin spiral, I know exactly the exchange parameter in the momentum space. I minimize under the constraint that the length doesn't change, and find basically that the minimum of the landscape of J of Q gives me basically the minimum of the energy of the Heisenberg model. This is true in the periodic system. So therefore, what I'm basically doing is I insert now a spin spiral in my density functional theory code and calculate for each Q vector in the two-dimensional or three-dimensional Brion zone the energy along paths and things like that. And the most obvious, if you look at the Brion zone, the most obvious point of minima and maxima are points of high symmetry. The X point, the M point, the gamma point. And they correspond to different magnetic structures. So the gamma point to the ferromagnetic one, the X point to the M point to the C2x2, and the ferromagnetic one, and so on. So I calculate now these things on the path. So if they are in the zone boundary, they are so easily periodic. If they are have a minimum in between, they are incommensurate. And by this, I get basically the lowest energy magnetic structure if the Heisenberg model is the dominant interaction. And the crucial thing is that these calculations are easy because I use the Bloch theorem. You remember the Bloch theorem makes everything, instead of calculating entire solid, I calculate only the solid in a unit cell. And now my unit cell is not only the unit cell of the crystallographic unit cell, but I'm moving and rotating. That is my symmetry. And this commutes with the Hamiltonian, basically gives me a generalized Bloch theorem. I not only have lattice periodic functions and a Bloch wave, but I have a Bloch wave for spin up and spin down, which depends on the spin rotation. And with this, I can calculate crazy spin spirals in a unit cell, in a chemical unit cell. So I exercise this here. For example, I have here a monolayer of chromium or manganese on copper. So I'm calculating here, it goes along this path gamma km gamma. So gamma km, and then back to gamma. And you see the lowest energy is the endpoint for manganese and copper. And then you see the endpoint is this one. And I have 6 of these endpoints. They're all degenerate. And I have here for chromium, I have the K point, and the K point corresponds to the Néel state, and the endpoint to this rho-wise antiferromagnetic state. So this is in the world of the Heisenberg model, this is the ground state. Now the next question is actually the Heisenberg model correct? This is a test. What I'm doing is I take my lattice and start by hand rotating the spins. For this, I do a constraint density functional theory. I basically do a constraint and follow the constraint and calculate the energy. So that's what I'm doing here. I take this periodic cell of atoms, and my unit cell here is maybe this 2 by 2 unit cell. I rotate the angle and calculate the energy as function of the angle. And this I do in this unit cell, and this I do in that unit cell as a 3 by 3 unit cell. And what I get is in this unit cell, I find 120 degree is the lowest energy. And in this unit cell, the antiferromagnetic one is the lowest energy, but it's higher than this one. And this I can fit with the Heisenberg model perfectly. Everything is super. And the J's are the same. Now I do the same thing for manganese. This is shown here. For manganese, I get the same picture. I rotate, I get a minimum for 180 degrees. But in the 3 by 3 unit cell, I don't get a minimum, which I should get if my Heisenberg interaction is correct. Instead, I get a maximum. And this I cannot explain with the Heisenberg model. In the Heisenberg models, I can only get even number of angles. So this odd number of angles, which is the cosine 3 alpha, that is missing. And it's missing because I have missed this particular interaction, which is this 4-spin interaction, which is relevant for this system. And with this 4-spin interaction, what happens is I go from the single Q state, which is this 1m, and the time inverse one. I have 3 of them as combination. With this 4-spin interaction, I get a superposition. I can get a superposition of the single Q state to a triple Q state, and this triple Q state can have a lower energy depending on the sign of Q1. And this is actually this state here, which was also found actually experimentally. So it is a non-complanar state. Now we know that it has topological orbital moment and things like that. The energy is actually quite large. It's 70 millieV per atom. All right. Now we can in principle do the same. How do we do in time, actually? Oh, I should finish. Okay, good. Let me say one thing, last thing. How should we, yeah, okay. I have another 100 transparencies, but you have to stop me. So basically, yes. How do we do it now? Yeah, we can do many things, but we could also do the same thing now to get out. So what is the Dzyaloshinskii-Moriya interaction? Dzyaloshinskii-Moriya interaction is just a spin-orbit contribution to the rotation of the winding of the magnetic structure. So basically, if we have now a spin spiral in the system, we are winding the magnetic structure. But then we have to calculate this spin-orbit matrix element. But unfortunately, the spin-orbit interaction breaks this nice symmetry which I have. This generalized translation symmetry works only without spin-orbit interaction. And if I have the spin-orbit interaction, so actually I'm scattering from K to K prime. So what I'm doing is now I take actually the spin-orbit interaction, to first do a spin spiral calculation without spin-orbit interaction. I get the eigenstates of the wavefunction eigenstates of the spiral for the spiral structure. And with this eigenstate, I do first order, second order perturbation theory. I set up these eigenstates a matrix, and this matrix I diagonalize. This matrix, of course, is huge, but it's sparse. And if I diagonalize this, then you see I get an energy as function of this Q vector. And then, for example, the curvature gives me the spin stiffness. The slope gives me the spiralization. And I think I should stop now and say thank you very much.